Hello and a warm welcome back. Today on the bench we've got this 2C34 push-pull parallel blah 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 AB2 amplifier. On the oscilloscope screen there you can see a waveform and it's distorted. If I turn that up more in amplitude you can see there's more shit going off, and that is with a output of about 12 volts, 8% THD. Now we've got 20 kilohertz, we're testing it at 20 kilohertz. I'll show you what I'm doing in a minute. Ooh, you fat pig. Okay, and that's at 5 volts RMS output, and as you can see we've got a really distorted waveform and it's jiggling about. That's only at 5 volts. And that's 12%. Let me just write that down. 5 volts, 12% minus 17. Yeah, so that ain't no freaking good, is it, to man the beast? So what I've been doing, I've got 3 different output transformers I can try. I've got the one that are wound, self-wound, which has got a primary impedance of 4K, or should have, but actually has a primary impedance, because I screwed up, of about 3.4K. And the other 2 transformers that I got are a 4K one, a proper 4K one, and a 6K6 one. And so I've just gone through them all, testing them at 100 Hz, 1 kilohertz and 20 kilohertz, and these are the results. So these are the results that I got from testing the 3 different output transformers with differing primary impedances. 6K6 at 100 Hz, it's 12.3 volts maximum output, and that's adjusting the you know, so that we get like a output that isn't clipping and looks good. 100 Hz 6K6 we got 12.3, same at 1 kilohertz, and we got the same, and I got the same THD, 7% THD. At 20 kilohertz you'll note that the output went down to 10.9 volts, and I got a THD of 3%. And then as you go down you will see 4K I got 13 volts, so a little bit more output power. Now 4K is the data sheet primary impedance that, you know, we should have. It's actually 8K, but because we are paralleling the output valves, then you halve it. So we got at 100 Hz we got an output of 13 volts, and if you'll notice, that's interesting, the THD has gone down to 4.7%, and we get the same result for 1 kilohertz, 13 volts RMS output for 4.7% THD. But however, when we get to 20 kilohertz you'll notice that it goes down to 8 volts, and our total harmonic distortion goes up to 8.7%. Lastly, the home wound output transformer, we got more output at 100 Hz, which is a bit weird, but I think that's because it's basically got a really big core, and the THD went down to 3.8%. 1 kilohertz we've got 12 volts RMS output, and as you'll see, look, the THD has gone up, and finally when it come to 20 kilohertz the output, as you saw, was horrible, and I had to reduce the input signal so that we got only 5 volts RMS output, and that was without it clipping and looking too horrible, but the THD had gone up to 12.7%. So as you can see, the best output transform for the job here, without pissing about and all the rest of it, is the 6K61. Hopefully you can also see that there is like a correlation, like a sort of seesaw effect between the total harmonic distortion at 100 Hz and 20 kHz. In case I haven't made it clear, what I'm trying to do by testing different output transformers is to try and get rid of the high frequency distortion. So as you can see on this oscilloscope here, this is the left hand channel, 1 kHz sine wave. I'm going to increase that to 40 kHz frequency. 40 kHz. And I hope you can see that the sine wave has started to turn more into a triangle wave. I shall try and show that clearer on the Tech 585A. So sorry about the wobble cam. Hopefully you can see the sine wave okay. On the top here, this is our input going into our first valve. That is 40 kHz. So that's a nice sine wave, and as you can see here, this waveform here is obviously distorted. I've been looking into this problem for a good few months now, reading quite a few books and articles on the matter, and as far as I can understand it, my best guess is that what I have is slew rate distortion. What is slew rate distortion? Every sort of device that's in here, be it the output transformer, the valves and other things like that, have all got a certain amount of capacitance. In the case of these 2C34 triode output triodes here, they have inter-electrode capacitances. I covered this on a previous amplifier. Here's just a rough depiction of a triode. So we have capacitance between the anode and the grid, and the grid and the cathode. There will also be some stray capacitances, which will be only a few picofarads, but that matters more as we get higher in frequency. If we think of this triode in simple terms as a capacitor, and then we have a signal coming in, this is our audio signal coming in there. If, say, at 100 Hz we are charging this capacitor up 0.1 times per second, so it's got a pretty easy life, yeah? But if we was to try to charge this capacitor at, let's say we're trying to charge this capacitor up at 10 kHz, then that means that our driving stage here has to work harder to charge this capacitance up, because instead of it trying to do it 100 times per whatever, you're trying to do it 10,000 times. Think of you trying to bounce a ball like on the ground 100 times and then trying to do that even faster. The amount of energy that you have to put in to get that ball to bounce up and down 10,000 times is a lot more. Does that make sense? Therefore, what slewing distortion is, it means that the driving stages of the amplifier, somewhere yet to be determined, can't charge whatever capacitance it is. I have a good idea it's the grids of the 2C34 output valves. It can't do that quickly enough, and so instead of us getting a nice sine wave like that, we're getting something more like that. So, and this is what, as regards sine waves, this is what you call the rise time from here to here. This is time going this way, this is amplitude going that way, yeah? If so, my hypothesis is, and from what I've researched, what the amplifier is doing, it's unable to provide enough oomph to make sure we've got a nice sharp rise time, and instead, like, it's sort of lagging a bit and it's falling off. I really hope that makes sense. It's something I'm not 100% certain of myself, but this is my understanding of it. On the oscilloscope screen there, you can see a waveform. I am scoping one of the anodes of the 2C34s. If I swing you back, so as you can see, it's distorted. What I'm trying to do is scope each stage individually to find out where the distortion is happening. So that's the anode of 2C34. Now I'm going to take that off there, and I'm going to ground my scope probe. So to discharge the cap, and I'm now going to put it on one of the grids of the same 2C34 amplifier, and as you can see, that looks fine. So what does that tell us? That tells us that the cathode follower stage can drive the grids of the 2C34s all right. However, when it comes to the anode, it's struggling. What the hell does that mean? Well, it must mean that the capacitance of the output transformer, the interwinding capacitance, is such that the two output valves can't drive it. So let's see if we can increase the quiescent current of the valves so that we get rid of it. See if that works. So we've got 3.6 volts distortion, 3.13, and this is at each valve bias stat minus 16 volts. I'm now going to alter that. I'm going to try and do this without getting about 3.76, 2.6. So yes, increasing the quiescent current of an output stage push-pull valve thingy does improve slew rate distortion. Right, just doing a few calculations. Setting the bias at minus 15 volts gives us an average anode dissipation of each one of these triode output valves roughly of 14 milliamps, which is a total of 4.4 watts. The maximum total power output of each one of those triodes is 5 watts. So 4.4 watts is getting a bit close to 100% dissipation. Normally I bias valves to about 75%. However, in this case, because like, you know, we've got more current flowing through each triode, we are at 90% maximum power dissipation. So whilst we are sort of okay, we're not really pushing it, the valves are obviously going to have a harder life if we set it to that. Before I found the missing jigsaw piece in Morgan Jones's book about increasing the standing current going through the output valves, I thought one probable cause of the high frequency distortion was because the cathode follower driving stage was driving two grids in parallel rather than one grid at a time. So, going back a few months, I tested the 10-watt version of this amplifier, and when I tested that amplifier I didn't have any of this high frequency distortion. Hence I thought, aha, right, what if I could drive each grid of the two C34s individually rather than together? And so what I did, I built these two double MOSFET follower McGubbins. Let's have a look at the circuit. Right, I shall try pressing record again. Just been waffling on for about the last 10 minutes. Oh, it's not easy being a YouTube video maker, you know. Anyway, what is a MOSFET source follower? Well, we just use a MOSFET, and as I mentioned, I used MOSFETs because it was a lot easier to build 4 individual source followers with FETs rather than valves. It's just the equivalent using a MOSFET instead of a valve for a cathode follower or a buffer stage, basically. Very low output impedance. That's what we want to drive the grids of the output valves. Using an IRF 840, and to set the bias for that, because like a cathode follower, the source follows the gate, we're just using a 100k resistor that I had already there, two 10k resistors, one from our negative 90 volt source from our minus 90 volt rail, 10k to ground. That sort of sets it about midway. We've got a 500k, or I suppose in this case it would be a gate resistor. With a valve it would be the grid leak resistor, and obviously that sets the gate, the source follows the gate, where we go. To make sure that we've got a lovely big bandwidth so that it can amplify all sort of frequencies from 20 Hertz up to, you know, I don't know, 50 kilohertz or more, say, using a very simple ring of 2 constant current sink. I mean, we could use a big resistor here, but the thing is with a resistor, to get it to approximate a really good constant current sink or source, I do have a problem with the fucking terminology, we would need to have a lower power supply, you know, something like minus 300 bloody volts, and a big resistor. Just easier to use a couple of transistors there. We've got the MGE340 high voltage transistor doing the sort of heavy lifting. This 140 ohm resistor here, that sets the current through all of this. And then this BC546, oh, that sets the current, by the way, to about 4.6 milliamps. 120 would have been better, but I didn't have one. This BC546, its base is connected to the MGE340's emitter, and so what happens is, if this starts pulling more current, then this turns on this BC546 harder, more current flows across it, meaning that the current on the MGE340's base is robbed by this turning on harder and brings it back into regulation. It's a very simple, effective circuit. Right, well I hope that explained things. Right, let's bang some music through the thing and then see how it sounds. Right, got some music going through the amplifier, just a quick music test. Oh, that sounds nice.
Yeah. Oh. Yeah, come on.
I'm a back door man. Right, well, that sounded alright. Let's see, where's the fucking lever? That sounded alright, lads and lasses. I've still got to build the bloody thing because this is still sort of in a prototype-ish configuration and what have you, so we're not out of the woods yet, but I think that is that issue solved. And now I know what slewing distortion is, and now I know what slew rate is. I find that I struggle with electronic concepts. I mean, it took me a long time just to understand Ohm's law. I can remember walking round and round a field with my dogs. If I over R, and where does this V come in? You know, shit like that. It takes me quite a long while to get there, but I get there eventually. So you got to stick at it is, I guess, the moral of the story. And if you stick at it and keep reading, you know, bits of paper and until like your head is like feels like it's popping with all the information in there, eventually you'll read a bit of information and think, ah, right, I got it, I got the fucking A. And then we test it out on the bench. Yeah, so I'm quite chuffed actually that I sorted that one out. I've just got a little bit of negative feedback applied at the moment. No compensating capacitors or anything of that nature. Yeah, I'm happy with it. I don't know if I went into like the MOSFET followers, hopefully I did. I'm still editing the video. Right, well thank you all very much for watching. Take care of yourselves. Ta-ra for now.